Okay, so we're looking at number 2.1.26. 2.1.26, and this is the triangle inequality for complex numbers. Prove it. So notice here that z is just a plus bi because it's just a complex number. And here we have w is c plus di for the same reason. It's just a complex number. So what we can do here is when we take the magnitude of z, so I'm looking at this part right here, and I want to know the magnitude of z. Well, the magnitude of z is going to be, well, okay, let's find the magnitude of a complex number real quick, just as an example. So let's say we have a complex number here, and that is going to be a plus bi. To find the magnitude of that, or to find this distance there, that hypotenuse, we just have to do the quadratic formula. So this is going to be a, this is going to be b, so b squared plus a squared is c squared, or c squared is, well, take the square root of both sides, and we end up with c is the square root of b squared plus a squared. Or you could also say that the magnitude of c is square root of b squared plus a squared. And you could also say that the magnitude of a plus bi is square root of b squared plus a squared, or a squared plus b squared. So that's exactly what I'm doing here. I'm just saying, well, the magnitude of z is going to be that whole Pythagorean theorem thing, or the whole Euclidean metric, or whatever it's called, that metric that decides how far things are away from each other. And you might notice initially, oh yeah, what the hell happened to those I values? So they were looking at the magnitude of something, which is only the distance from the origin, which does not have an imaginary number associated with it, even though the number itself does. Even though this number does, the magnitude of it does not. So when we're looking here, that's why we don't have any i's involved in that. Okay, so the first thing we do is we say, okay, there's too many square roots, let's just square this thing. And so at this point we just square it, and we get rid of a square root in the process, but we have a little bit left over. We cancel out some things. Notice here we are canceling out a whole bunch of stuff. Like this d squared here cancels out with this d squared. So an a squared, b squared, c squared, and a d squared all get canceled out. So right, all these guys. And then at that point, we just have these left. So I'll make these in blue. All we have is these left. And at this point, I want to get rid of the square roots again. So all I do is square both sides again. So we end up with what you see at the next line here. So at that point, I just cancel out some more. Subtract, for example, subtract this 4a squared c squared from both sides. This one, subtract from both sides. This one, subtract from both sides. And then we're left with this. So we're left with this one right here. And then I'm immediately noticing, oh, hey, look at that. That looks like that looks like a square to me if I subtract 2abc from both sides. And that's exactly what I do here. Then I turn it into a square, an obvious square. And then we see here that we have some number squared. And that number there is going to guaranteed to be positive, or it's going to be greater than 0, which is exactly what we wanted to prove. We wanted to prove that is true, that this inequality holds throughout the whole situation. So Yes, yes, yes. This inequality holds. And so we could zoom it back up, and so then also this inequality holds, and you could write a bit of an explanation there. But yeah, that's basically it.